The greatest of human endeavors is a risky business.
Yes, we've had a problem here.
NASA led the world into the exploration of space, but behind the scenes, out of the public eye, mistakes, mishaps, and failures plague the space industry.
Obviously a major malfunction.
Discover how NASA space failures further exploration. January 16, 2003, Space Shuttle Columbia lifted off from Launch Complex 39A at Kennedy Space Center. 16 days later, after completing the mission objectives, Columbia broke apart during re-entry, resulting in total loss of vehicle and crew. For 2.5 years, NASA's launch pads sat empty, a solemn reminder that space is a risky business. The shuttle fleet was grounded, and the world wondered if NASA would ever launch another space shuttle. Behind the scenes, NASA worked tirelessly to return to flight. NASA undertook a massive recertification and verification process that evaluated all of the space shuttle's critical systems, while at the same time addressing external tank foam debris, which was determined to be the primary cause of the accident. NASA set May 2005 as the target launch window for return to flight. But when a critical external tank test fails, NASA scraps the launch date and is forced into a new investigation that reveals a tangled web of space mistakes that threaten to once again derail the entire Space Shuttle program. But first, during the orbiter recertification process, a chilling space mistake was uncovered when a rudder speed brake actuator was opened for the first time in 20 years. When the orbiter returns from space, it becomes a high-tech glider during descent and landing. With no power, slight course corrections and deceleration maneuvers are performed using the wing and body flaps and the rudder speed brake. The rudder speed brake is controlled by actuators in the tail section. As the orbiter approaches the landing strip, the rudder speed brake is used for aerodynamic braking to aid in slowing the orbiter. At a descent angle 7 times steeper than a commercial aircraft and traveling 220 miles per hour, the rear wheels touch down. A drag chute is deployed, followed by the nose gear touchdown. The rudder speed brake is then fully deployed. 30 seconds later, the orbiter has slowed to less than 68 miles per hour. The drag chute is released, and the orbiter coasts to a stop. During recertification, all 3 orbiters, Discovery, Atlantis, and Endeavour, reside in orbiter processing facilities 1, 2, and 3 at Kennedy Space Center. Surrounded by access platforms and support structures, the orbiters are barely recognizable. New carbon fiber material is being placed on the wing leading edges and nose cone sections. Thermal protection system tiles are replaced by hand, and landing gear systems are tested. The return-to-flight launch window is now less than a year away. NASA works multiple shifts in their attempt to complete all the required work on time. At the highest platform level, the tail of Discovery rises majestically above the mayhem. The actuators that control the rudder speed brake are to be checked next for recertification. The tail section contains 4 rudder speed brake actuators controlled by a power drive unit. Each actuator contains an inboard set of 9 planet gears and an outboard set of 9 planet gears. 2 shafts connecting the actuators to the power drive unit control the actuators, which work together to open and close the 2 speed brake flaps. But when the actuators are opened up, engineers are astonished to discover corrosion in the actuators and gears. But even more shocking, they discover that one of the actuator's planet gear sets are reversed.
As we were exploring where the corrosion was and what caused the corrosion, we noticed that the wear marks on the gears didn't line up just the way we thought they should. And it was at that point we discovered that we had reversed the planet gears.
There are 2 sets of planet gears, and they have been installed in the reverse direction from how they should have been. Basically, they've been swapped out.
An analysis of the gears revealed that the outboard gears were slightly smaller than the inboard gears. When configured correctly, 9 of the smaller gears are in the top or outboard half of the actuator, and 9 of the larger gears are in the bottom or inboard half of the actuator. However, engineers discovered that in one of Discovery's actuators, the 9 smaller gears were in the bottom and all 9 of the larger gears were in the top. If the rudder speed brake fails, Discovery, Atlantis, or Endeavour could be destroyed on landing. Return to flight just got a lot more complicated. With return to flight activities rushing forward, a new investigation is launched to determine how the rudder speed brake actuator, or RSBA gears, could have been reversed. The mistake also raises concern for the gears on Atlantis and Endeavour. The incorrectly installed gears reduce the overall strength margin of the actuator.
You don't get full tooth engagement. You've only got part of your teeth engaging, therefore it results in a higher stress state for the gears that are engaged.
And could result in a critical failure if the gears fail during flight. The orbiter would land traveling much faster than normal. When the drag chute deployed, the air resistance would have been too great, forcing the nose landing gear to slam into the ground. The massive high-speed stress would break the landing gear, resulting in the nose hitting the runway and the orbiter losing complete control with catastrophic results. Even if the issue was noticed in time and the drag chute was not deployed, the increased landing speed could have caused the orbiter to exhaust the entire runway, crashing in the swamp on the north end. The rudder speed brake is a single point of failure and could not be more critical to the landing sequence. But Discovery had flown 30 missions and landed successfully each time. Further investigation revealed that the gears in the other 3 actuators on Discovery were installed correctly. This time, NASA caught a break.
We were lucky in this case that it was the lowest loaded actuator that was put together incorrectly, and as a result, we didn't have any problems.
Because the only actuator that was affected on Discovery was the highest actuator out of the 4, it bore the least amount of stress during speed brake operation. The wear and tear on the gears was evident, however, and could have been just a matter of time before the gears failed. Atlantis and Endeavour were both inspected. NASA is relieved that no other Planet gear sets are installed incorrectly. However, when NASA begins to replace the worn-out and misassembled actuator with a spare actuator, they discover the same problem in the spare unit. Engineers immediately began to develop solutions to make sure this space mistake never happens again. An extensive investigation revealed that during the original assembly of the gears into the actuators, technicians became confused for 2 reasons. First, the gears in each of the 4 actuators are all installed differently because each actuator supports different loads. An analysis revealed that if the gears in the incorrect upper actuator, actuator number 4, had been installed in the actuator 1 position lower in the actuator 3 housing, then surprisingly, the gears would have been in the correct position for that actuator. It was surmised that the technicians may have assembled the 3rd actuator and then assembled the 4th using the same gear order. Secondly, the top and bottom gear sets look almost identical in size. To eliminate the confusion, engineers developed special tools for each set of Planet gears.
As part of our mistake-proofing process, we actually went back and designed dedicated fixtures to each actuator that also have physical limitations such that if you use the right tooling for the right actuator, you'll be unable to assemble it swapped out gear sets.
This example of mistake-proof engineering eliminates any guesswork because one tool can only be used with the bottom gears, and a different tool can only be used with the top gears. This ensures that the gears cannot be installed incorrectly again, as long as the technician uses the newly designed tool. The spare actuator unit was repaired successfully and installed on Discovery. The remaining mystery was why had this problem never been noticed before?
The initial requirement for the rudder speed brake system was 100 missions. However, the time for that was 10 years. Now, as it turns out, we went 20 years without looking at them.
The mistake was not found sooner because the actuators were certified for the original flight life of the Space Shuttle, 10 years, 100 missions. Due to budget constraints and realigned program objectives, the Space Shuttle flight schedule was never as aggressive as anticipated when the program began flying in 1981. So although the affected actuator had been installed for double the 10 years, it had only flown 30 times, so it was still considered under the original certification. NASA learns from their mistakes and is applying these lessons to the new exploration programs.
When you manufacture something as critical as the flight control surface actuators for those things like the Space Shuttle, they have to work. And they have to work consistently, and they have to work every time.
Create mistake-proof designs such that put components in that can only be installed one way, take out the human element that could potentially make an error putting that together.
Look at how you're going to assemble things. We tend to have engineering tends to dominate the design, and without necessarily considering all the implications of assembly.
With the RSBA issue resolved and the massive recertification effort now complete, a launch date is set. Discovery is mated to a new external tank and solid rocket boosters and prepped for launch. Finally, the Space Shuttle's long-awaited return to flight seems imminent, until a shocking discovery reveals a space mistake with disastrous consequences. NASA sets May 2005 as the target launch window for return to flight. Kennedy Space Center buzzes with excitement as the long-awaited return-to-flight launch window finally approaches. It has been an arduous 2 years and 3 months since a space shuttle has flown. But just as NASA is poised to overcome the tragic loss of Columbia and get back to the business of building the International Space Station, 700 miles away on the edge of the Louisiana Bayou, a phone call is about to change everything. NASA's Michoud Assembly Facility, or MAF, held the world's record as the largest enclosed building on Earth for over 20 years. It is hallowed ground in the space industry. MAF was the original manufacturing facility of the massive Saturn V rocket, the rocket that carried the first humans to the moon. The Space Shuttle is comprised of the orbiter, the Space Shuttle main engines, the solid rocket boosters, and the external tank, or ET. The 154-foot external tank supplies fuel to the Space Shuttle main engines during launch and ascent. The aluminum lithium alloy tank is comprised of 2 fuel tanks. The forward tank, called the LOX tank, contains 146,000 gallons of liquid oxygen. The rear LH2 tank contains 395,000 gallons of liquid hydrogen. MAF was the obvious choice to manufacture the Space Shuttle's external tanks. Some of the largest tools in the world were constructed inside the facility to build the massive liquid oxygen and liquid hydrogen tanks. Unlike the solid rocket boosters, which are retrieved, refurbished, and reused after every launch, the ET is disposable, splashing down and disintegrating in the Indian Ocean. So every Space Shuttle launch requires a new ET. MAF is a busy place. Prior to Columbia, 113 completed external tanks rolled out of MAF were loaded on specialized barges, then transported by water along the coast of the Gulf of Mexico, around Florida, and delivered to Kennedy Space Center. After the Columbia accident was blamed on foam loss from the external tank, morale at MAF has been low. With return to flight approaching, a renewed optimism is returning. But less than 45 days before the launch date, a company interested in supplying a metal screen material used in the external tank contacts engineers at MAF with a disturbing discovery.
When they compared that screen they were going to buy with the screen that was on existing parts, they noticed there's a difference.
The company was interested in creating and supplying the screen material used on a critical piece of hardware called a diffuser. The diffusers are used in the top of both the liquid oxygen tank and liquid hydrogen tanks.
When we launch, the liquid level of the tanks start to drop. And so we put ullage pressure back into the top of the tank. When the liquid level is dropping in the tank, you're forming a vacuum. So you don't want the tank to collapse on itself, so you're putting pressure back in through the top. And the diffuser disperses it into the tank so it doesn't all go in one spot, cause something to be too hot, one area too cold.
As the liquid hydrogen and liquid oxygen are consumed during launch and ascent, gaseous hydrogen and oxygen are pumped back into the respective tanks. The gas is dispersed by the diffuser at a finely calibrated dispersion rate, matching the drain rate of the liquid fuel. If the rate is off or restricted, the massive vacuum pressure inside the tank would begin to resist the fuel flow and could cause the tank to collapse, creating a catastrophic failure. The company interested in supplying material for the diffusers had requested several samples of the screen material to determine if they could meet the specifications. But when they analyzed the samples, they discovered that there were 2 different types of screen material. With Space Shuttle Discovery fully stacked and almost ready for flight, NASA launches an emergency investigation. Which screen material was correct? Were any diffusers made with the wrong material? And if so, would it affect their performance? And most importantly, which material was used on the diffusers in the external tank currently scheduled for launch? The specter of a delayed launch began to overshadow NASA's imminent return to flight. And for this space mistake, the worst possible scenario was about to come true. A company interested in supplying the screen material for the gaseous hydrogen and gaseous oxygen diffusers used in the Space Shuttle external tanks discovers that two different types of material were provided as examples of the required screen material. The diffuser is comprised of a hollow metal core with a wire mesh screen around it. The design of the mesh is known as a plain Dutch weave. When the company analyzed the two screen materials, they discovered that some of the material was the required plain Dutch weave, but the other samples were a duplex plain Dutch weave.
Using unaided eye, you will not be able to see a difference in these two screens. But if you held a piece of the sample or sample of the material in your hands, you would notice that one was slightly stiffer. And then if you used magnification, which we found at least 10x, you could see that there was a different amount of wires per inch.
So when you have a weave of screen material, you have one wire that I guess you would call static or a warp wire, and then the other wire bends around that. So a plain Dutch weave has one wire, and then the other wires get bent around it. A duplex has actually two wires, and the wire gets bent around it.
Through analysis and testing, the investigation team confirmed that the duplex plain Dutch weave was not acceptable because it would restrict the uniform flow of ullage pressure and gases, restricting or stopping the flow of gases back into the tank while the liquid fuel rushes out to fuel the Space Shuttle's main engines could cause stress on the tanks and even the catastrophic collapse of the tank. Even with a minimal reduction in ullage gases, the vacuum inside the tanks could restrict fuel transfer to the main engines, which would not allow the orbiter to complete launch and ascent, resulting in a catastrophic failure and loss of vehicle and crew. NASA's investigation team begins to work around the clock to determine if any one of the diffusers currently installed in external tanks were made with the wrong screen material. While they can test the assembled diffusers in inventory by direct analysis, the diffusers inside the completed external tanks could not be accessed. Shocked, the investigation team discovers that 15 of the 21 diffusers in inventory were constructed with the wrong material. The likelihood of faulty diffusers in completed external tanks was increasing. The investigation team traces the wrong material to a different company that had supplied screen material years earlier. That company delivered both the correct plain Dutch weave and for some reason also supplied the wrong duplex plain Dutch weave under the same part number. Then the company went out of business, which was why NASA was seeking a new supplier for the screen material in the first place. As the feverish investigation continues, Space Shuttle Discovery is moved to the launch pad. But are the diffusers inside the external tank faulty? NASA needed answers, and fast. While the investigation reaches a feverish pitch at the Michoud Assembly Facility in New Orleans, Discovery begins launch preparations at Kennedy Space Center in Florida. The shuttle is moved to Launch Pad 39B, and on April 14, 2005, a critical tanking test is performed. The test is standard procedure in advance of a launch, but today's test is anything but standard. The external tank is filled with liquid hydrogen and liquid oxygen, and as Mission Control begins testing, a liquid hydrogen pressurization relief valve begins to act strangely. The valve is designed to open and close to ensure the liquid hydrogen stays at the correct temperature, but this time it is cycling more often than normal. Then suddenly, engineers begin receiving intermittent readings from the liquid hydrogen sensors. The sensors serve as fuel gauges and are responsible for sending the signal to the main engines when the fuel is depleted and the engine should shut off, called MECO, or main engine cutoff. The test is a failure. Afterwards, a full system check and analysis indicate the probability of a problem with the hydrogen tank diffuser. The mid-May launch is scrapped, and in an unprecedented move, the fully stacked space shuttle is returned to the vehicle assembly building. NASA's celebrated return to flight remains elusive. Meanwhile, back at MAF, The investigation team concludes a thorough review of the documentation created during processing of all of the diffusers. They were able to identify which rolls of the screen material were wrong, and then track it through the assembly and installation process to discover if any diffusers in completed external tanks contained the faulty screen material. The results were disheartening.
In inventory and installed on tanks, we had 31 diffusers that were made out of the wrong material.
It was 21 GH2 and 10 GO2.
Out of 26 diffusers installed in 13 completed external tanks, 16 diffusers are faulty. And unfortunately, the team confirms that the hydrogen diffuser in Discovery's return-to-flight tank is also one of the faulty diffusers. Back at Kennedy Space Center, the Space Shuttle is destacked for only the 8th time in the program's history. All the return-to-flight momentum seems to have dissipated. A recovery plan is quickly put in place. Because of the failed tanking test and other issues, NASA does not want to use Discovery's tank. An external tank for Space Shuttle Atlantis is already at Kennedy Space Center and stored in the Vehicle Assembly Building. Its diffusers are faulty as well, but MAF sends a team of 30 engineers and technicians to replace the bad diffusers. This will be quicker and less risky than shipping another tank by barge from MAF. Also, the extra tank is already prepped to all the return-to-flight certification requirements and is essentially ready to go.
30 people went down to the Cape for us to go down and remove and replace those diffusers, which was something we've never done before. Remove and replace the diffuser at the Cape, it's never happened before. Whole new learning curve. Actually, I think it was a learning curve just trying to remove and replace one here, because we've never done it before.
Because the company that supplied the incorrect duplex plain Dutch weave went out of business, the investigation team could not discover why the wrong material was delivered. NASA learns from their mistakes. All future screen material was inspected by magnification to confirm the thread count and wire configuration, even if the paperwork says it's correct. The specification paperwork was also updated to clarify the demand for a single static or warp wire and not a double wire. July 26, 2005. Once again, the world watches as NASA makes another attempt to return to flight. Tension is high. In a little over 3 months since the failed tanking test, Discovery is once more poised for launch. As the crew heads to the launch pad, NASA's engineers and technicians, along with all the companies that contribute to the Space Shuttle, watch in hopeful anticipation. It has now been 2 years and 6 months since the last Space Shuttle slipped the surly bonds of Earth. But today, the Space Shuttle would fly once again. The successful return-to-flight mission led to the full reinstatement of the orbiter fleet and resumption of a full flight schedule. NASA was founded on the principles of exploration and pushing the limits of human achievement. As astronauts place their lives in the hands of engineers, technicians, and managers, mistakes will happen, but the lure of the unknown and the thrill of discovery continue to inspire humans to develop safer, more powerful spacecraft and to reach beyond our planet to the stars, to go further and discover more.